So I hope you're all working on your project proposals. I think as of now, there were 32 submissions in. That was last night. There may be a few more now. Since you're all submitting individually, there should be about 120 by Friday, I believe the deadline. Is that right, John? The deadline Friday? Yes. So keep them coming in. I've been seeing the papers so far. I did one quick scan last night. They're mostly good. They're mostly good suggestions that people have. There may be a little bit of things I would suggest one way or the other to maybe modify or think, but for the most part, I think you're on the right track. So I'm very happy about that. It's very interesting to see the kinds of papers you chose, and I almost want to ask, so why did you choose that one? Not because it's a bad choice, it's a good choice. But I'm just curious as to what made you think to choose a particular paper. If someone wants to share, I'm curious. Someone who's already put a submission in, would they like to share why they chose a particular paper that they did? Anyone? Anyone have any comment on the paper that they chose? No?
I have a question.
You have a question? Okay.
Can we choose like any algorithm which is not written in paper, but it's a well-known algorithm, but
Like what?
like pyramid algorithm,
What's a pyramid algorithm?
dynamic programming, but in the form of pyramid for drawing curves and stuff. It's for drawing Bezier curves and stuff.
I'm inclined to say no, unless there's a good reason to say yes. So, based on the information you give me, I'll be leaning more towards no than yes. Because I would like, it's not that I think that papers and conferences are like awesome sauce and everything else is, but there is some kind of baseline level of complexity if a paper is being published in a conference that guarantees a certain baseline level of effort required to do it. If something is not published, it has to be a very case-by-case thing. And the description you've given me thus far is not convinced me enough. This is more than just something you can throw into a HOPL lecture. So no one wishes to volunteer any information about how they chose the paper they chose? That's a very nice suggestion on that. So, I mean, don't be shy. I'm just curious. No one? I mean, I hate to pick on someone because, it's a random paper just stuck in my head and the person's not going to be happy. But someone chose like the MapReduce paper. Was it Did you choose the MapReduce paper?
I think so.
The Vasilevsky-Karlov Suri paper?
What I wanted to do was something that was published in 2014, and I was discouraged from that because we had to cite other references.
Why did you want to choose something that was published in 2014?
Because it talked about in-place transpose on the GPU, which could save memory.
Okay. So you changed this other thing, which is still in the realm of changing the model of computation and thinking about what happens when you change the model of computation and you design algorithms for the model, which is a paper that I see. Any other comments on things you chose or were sort of suggested? I mean, this is a good, by the way, if you were told not to choose Bureau 2004, it's a good suggestion not to, because it's too new. And that Any other?
So Roy was the inspiration behind the second paper.
Who?
Roy.
So tell me what made you think of that?
Well, when we were talking about the Fibonacci sequence,
Yes.
and looking at memoizing versus pointer redistribution, I was wondering how that might get represented and work in a parallel system.
Okay.
So I found the MapReduce paper. I thought, well, I wonder how algorithms hold up in distributed systems.
That's a very good paper because it basically it wasn't the MapReduce paper itself, and in fact another group has proposed the MapReduce paper itself, but I may have to have a few words with them about that. But this paper actually looks at a theoretical model for trying to understand cost on a MapReduce type system. Right? If you have a MapReduce type system, you can't use cost and running time in a normal sense. It doesn't make any sense anymore. So you have to change the notion of cost. So what is a good notion of cost to capture accurately what's really happening, and then what problems become easy and hard now. So it's going to be quite interesting to see. Okay, good. All right, so let's continue the lecture today. We were looking at greedy algorithms last time. Apart from my sort of initial disparaging remarks about never using greedy algorithms, the reason why they're attractive again is because they're simple and they're local. Like they have the feeling of do something that feels good right now, and then keep going. It's a very simple idea. And in both the examples I talked about last time, there was a sense of you have to either keep ahead of the optimal solution, so that at all points you're doing at least as well as optimal, which means at the end you are optimal. in terms of cost at least. Or there was a sense that you were looking at some interesting structure that all optimal solutions had that you could exploit. And then you could reason that if the optimal solution did not have that structure, you could in fact prove that it could use that structure without changing its cost or without increasing its cost. In particular, we looked at this problem of scheduling, where we said, if you want to schedule jobs and they have deadlines, you never need to, if you schedule jobs in the order of the deadlines, that's enough. And the proof was basically saying that if you actually reverse two jobs, if they were not in the order of their deadlines, you could change them back and you would not increase the cost of your solution. So it is a very indirect proof, right? The algorithm itself just said, sort them by deadline and schedule it. But the proof said, if in fact this was not the right thing to do, you could make it the right thing to do. So the proof was sort of more complicated than the algorithm itself, because you're trying to reason about the optimal solution. So this would give you the impression from both of these that, a lot of times a greedy algorithm involves looking very carefully at the right step to take down a slope, the steepest step, or the best in some sense, right? Do what's best for you right now. But a very important part of a greedy algorithm is not so much the idea that you must do what's best for you right now, but that the problem admits such a nice structure that as long as you do something not unreasonable right now, you'll be fine. Which is quite different to saying do the best thing. Just saying do something that's not unreasonable is very different. It's much easier in some sense. And it still gets you to the right answer. And in a sense, that's a more honest way of describing how greedy algorithms work. And that's because there is a topic, and I've had notes on this in the syllabus, but I'm not going to talk about this in class. There's this way to say, when does a problem admit a solution that's a greedy algorithm, and when does it not? And in fact, there's a fairly decent characterization of when a problem admits a greedy solution that's optimal. It's when the problem is something that's called a matroid. And it gets an algebraic structure like a group or a field that I don't want to get into. But the main characteristic of such problems is that if there's an optimal solution, and there's where you are, there is always a way to get closer. Not the best way to get closer, the fastest way or whatever, but there is some way to get closer. And that's all you need to justify a greedy algorithm. That there's always some path. You never get stuck in a dead end. And the essence of being greedy, or when greedy works, is when you can make that statement. That you never get stuck in a dead end. There's always a way to make progress. Like when you're going down a slope, right? If you go down a slope and you want to get to the bottom, you will always make progress as long as you don't get trapped in something in the middle, a lower dip somewhere. And that's the essence of it. So it almost doesn't matter how fast you go or how well you do it, then there should always be a path. And today's lecture will show you examples where we're going to talk about a problem which admits what might not typically be what you think of as a greedy solution, but does admit local solutions where you make a local decision and there's always a way to make progress. And in fact, the matroid structure of problems that admit greedy is very clear in this problem, but again, we won't talk about this in this class. There are notes that you can read that are very interesting if you want to know more. And the problem is a problem that you may have seen before, it may be very well known to you, the problem of spanning trees. Right? So what's a spanning tree problem? In a spanning tree problem, I give you a graph. So I have, let's say I have a graph here. And again, there are notes on all this in the syllabus, so you don't have to copy it down. Right? I have some kind of graph, and I have weights on all the edges. That's when I pretend I don't have weights. Right? Just when I have a graph. What I want to do is compute a tree, which of course is a graph with no cycles in it, a connected graph with no cycles in it, that connects up all the nodes. Why? Because I wanted to connect them up. Maybe I have a routing protocol, I want to be able to have them all be able to talk to each other. Maybe I want to build a road network so all the nodes can reach each other. But I want to do it as sparsely as possible. Of course, a tree is the sparsest thing you can do. And what would a tree look like here? If I change to, let's see. So a particular tree might be something like this, this. It's a tree because, well, it's a tree. It's a spanning tree because it touches all the nodes, right? A spanning tree. And what you want in general is a spanning tree of minimum cost. What does that mean? Well, you can think of if you're laying pipe or laying a road, the cost of laying an edge is the length of the edge. So if every edge is a length of this graph, what you want is to compute is some tree of minimum total weight. So you add up all the weights of the edges in the tree, and you want the cost to be minimized. So let's say, let's say I have a weight function. So I have a graph G with vertices and edges, and I have some weight function from the edges to the reals, and these are positive weights, right? And I want to find the spanning tree. As I said, a tree that connects all the nodes of minimum weight, where the weight of a tree is equal to the sum over all edges in the tree of the weight of that. Okay? Many of you, if you've taken an undergrad degree in computer science, have seen minimum spanning tree algorithms, or at least heard of them. Oh, pardon me? Yes? Sorry?
You use a depth first search or depth.
That'll give you a tree. Definitely. That'll give you a minimum spanning tree. That'll give you a spanning tree. Yes. You can use a DFS or a BFS to find that. Someone else had a hand up somewhere. Yes?
Isn't this essentially finding the shortest point from one particular node to all the other nodes?
Finding the shortest what?
Shortest length, or shortest weight path.
Is it the same as finding the shortest length paths from one node to all the other nodes?
Maybe.
I don't know. Is it?
I'm going to guess yes and think about it.
We never guess. But it's a good guess to try and think about. So the point is, if you make a concrete statement like that, then it's falsifiable. But you can think about whether it's true or not. So that's good in one sense. But think about that. That's a good question. I suggest you all think about this. In other words, is the minimum spanning tree the same thing you'd get if you picked a node and took shortest paths from that node to every other node?
No.
Well, first of all, would you get a tree if you did the second thing? If you took a node and took shortest paths from that node to all of the nodes, would you get a tree? You would? Not sure? Would you get a cycle? Assume all edge weights are distinct.
You wouldn't get a cycle because you'd just be going back to yourself.
No, you can get a cycle.
So, are you saying you could get a cycle?
Yeah, I think so. I mean, it seems reasonable that you could get a cycle out of that. If you're
It
saying,
seems reasonable as a standard. We're not allowed to apply
okay,
this.
yes, you could get a cycle. You'll get a cycle
Prove
probably.
it.
Okay, so let's say, for your example, right?
Yeah.
You could go to, well, okay. You could have a cycle. Okay. Well, let me think about it. I'll get back to you.
Yeah.
See, cycle would mean you're not taking the shortest path, you're repeating over something.
So suppose I have a cycle in this shortest path network. That means I have two nodes and two paths between them because there's a cycle. One of them is shorter, right? So either they're both equal, in which case I take one of them. Or one of them is shorter, in which case I should take that one. Don't be so sugared. I mean, it was a good guess. But when you think about it, then that's what will happen. So you won't get a cycle, so at least you get a tree. So at least it's a tree. Is it a spanning tree? Well, yes, by definition. You're going to construct paths to everyone. So it's a tree, it's a spanning tree. The only question that remains is it minimum? And I'm not going to answer that question right now. Think about it. Think about whether this claim is true, that the minimum spanning tree is equal to this.
I vote true.
This is not democracy. Mathematics is not a democracy. It is for entertainment value, but not in reality. Okay. So, so the problem, of course, is can we design an algorithm to compute shortest paths? To compute the minimum spanning tree. Can we come up with one to compute the minimum spanning tree? And so, it turns out that there are some very simple observations you can make about what a good spanning tree must look like in order to have any hope of one day being optimal. Right, so you have these little baby spanning trees and they want to grow up and become optimal minimum spanning trees. They have to have some properties, right? And it turns out that that's all you need. And as long as you have those properties, they will continue to grow. And they can continue to grow and they will become optimal. And it's a very beautiful set of properties. And it turns out, and this is one of those things that it took about 100 years for people to figure out. Mainly because of Cold War and other things that there are some very simple facts about spanning trees that once you state, many different kinds of algorithms automatically become correct. They have different running times, but their correctness is almost guaranteed by these observations. Okay? So let me tell you what these two observations are. So the first observation we're going to make, so we're going to start off with, all the algorithms we're going to discuss are going to look like the following. So the generic algorithm, so this is what a generic MST, minimum spanning tree algorithm. Okay, so it'll be something like this. Start with one vertex or edge and start growing. Okay, so at some point in the process, you have some intermediate representation. You have So does everyone know what a forest is? A tree is a connected acyclic graph. A forest is a collection of trees. So they might be disconnected, but there's a whole bunch of trees. So what's going to happen is at some point in the algorithm, we're going to have a collection of trees. And then we have to decide how to take the next step towards connecting them up. Because in the end, you want one single tree. Right? So you have a forest at some point, and then you add some new edging. And then repeat till you have that's it. All the algorithms we'll see today have this flavor. Okay? So you start off with a seed, which is one vertex or one edge, as the case may be. And then you just sort of grow things. And this, in some sense, is the greedy-like step. The step here is basically saying, I can keep adding something to my current state. I don't have to go back and change my mind. If you think of, for example, how a dynamic program works, you're constantly changing your mind. You keep building up these subproblems, you keep routing, and at some point you realize, okay, I have to reroute. You're effectively rerouting some other way, and so on and so forth. In a greedy algorithm, you never change your mind. You build something, you make a decision, you move on. And so this is the greedy step in some sense, that you're adding some new edge in, and you keep going through it. Okay? All right.
Excuse me.
Yes.
In first step, we need to find the minimum weighted edge, right?
So notice that I haven't yet said anything about minimization. In fact, you could start with anything you want. You could start with anything you want, and I haven't even told you how to add a new edge. It will turn out that the rule to add new edges in will automatically guarantee minimality without explicitly ever saying anything about it. And you will see in those books. It does kind of, but it's low. It's getting low. Okay? So the key step here to make this into an actual algorithm as opposed to just some kind of high-level hand wave, I have to tell you how to do this thing. On what basis do I add this new edge? I can't add any new edge in. That's not going to work. I'm going to add new edges chosen in some specific way. And to do that, I need to tell you which edges are good to add in, which edges are bad to add in. There'll be edges that are neither good or bad. Yet. Okay. So there are two properties we're going to use. So again, remember that we have a forest. At some point in time, we have some kind of forest associated with our algorithm. So let's say this forest F consists of some tree here, there's some tree here, maybe there's something here, something like this. So this is my current state of the input right now. I have these four components in it. Okay? I'm going to define two kinds of edges. So the first edge I'm going to define now is what I'll call safe edge. And a safe edge is an edge which goes between components. Okay? You see that? Yeah. It's always an edge that goes between two components. Okay? And it has the property that, and this is where we use the weight, it's the min weight edge out of a component. Okay. So notice that for each component of this forest, there is exactly one safe edge, assuming all edges have distinct weights. Because it's a minimum weight edge that's going out of it. That means it has exactly one edge going. Okay? So that's the first kind of edge. The second kind of edge we'll define is the opposite of safe. Well, opposite of safe would be dangerous. It's not dangerous so much as worse than dangerous. It's useless. And it's basically any edge inside so any edge not in F, that's not an F inside a component. So in particular, this would be a useless edge, right? So any edge between two vertices that are inside a component is useless. The min weight edge exiting a component is safe. Okay? So why do I care about these two things? What do you think I might, can I say anything about these two kinds of edges? And what kind of role they might play in the optimal solution to the spanning tree problem? Yes?
I guess you want to pick a safe edge that isn't a useless edge.
You want to pick, can a safe edge ever be useless?
Maybe.
Yes, could become.
So I hear yes, maybe, and no. So who said yes? Yes.
It could become like.
No, at any point in time. Well, think freeze a point in time. Can a safe edge be useless? Like right now. Well, I agree that things can change as time goes on, but right now, can a safe edge be useless?
Doesn't
So someone said no. Who said no? Anyone who said no? Yes.
because the safe edge goes out of the component, the useless edge is inside of the component.
Yeah. So at any point in time, a safe edge is not useless and a useless edge is not safe. But as you all are thinking now, if I start adding edges in, this will change. This is true. But can I say anything right now? See, right now I'm not going out of it. I have to decide what to do right now. Yes.
So all the trees that you have consist of safe edges.
All the trees that we have consist of safe edges.
Because we connect two things with a safe edge. So
Oh, wait. Okay, good. Repeat that sentence. We
So-
connect two things with safe edge. Why?
because we want to have a minimum edge.
So you are not making a very important claim. You're not asserting a fact, but you're making a claim. And the claim you're making is you only want to use a safe edge to connect two components as you grow the tree.
Because it's reasonable.
Doesn't
Reasonable.
Because it's reasonable. That's not good enough though. We want to be more than reasonable. We want to be right.
but a useless edge introduces a cycle, right? And you can't have one of those.
Good. So good. They're all bubbling up. This is very good. So push that safe edge discussion on the stack for a second, because we just made an observation about useless edges. You don't want to put a useless edge in your tree because it will cause a cycle. You can't. In other words, you can. If you've already committed to the forest you have right now, you do not want to add a useless edge to this forest because it would add a cycle. That's why they're useless. That only works if you're right so far, of course. If you made a mistake, then you want to. But now we get back to the point. There was a hand up somewhere there? Okay. The claim being made is that you only want to add safe edges to your as you grow. In other words, another way of reformulating that is every minimum spanning tree contains every safe edge. Why is this true? Or why would this be true? Not why is this true. Why would this be true? Or why could this be true? Or is this true? Yes?
That's the way we create trees. First of all, we have.
I create trees by planting seeds. I don't know. No, I'm just kidding. What I'm saying is I don't know what you mean by creating trees.
So when you want to actually link two things to each other, I mean, initially we don't have any.
But again, this. By the way, this is a very good point you're making, because to me this shows the insidiousness of green thinking. This is the way we do it. We join things that are the best. But why? Why is this the correct thing to do? You can't just say, well, that makes sense because I want to get the smallest thing. You don't know if your choice right now is going to make some future edge useless that you should have added in. Because when you join two components together using this mid-weight edge, they are now together. There was some other edge between them that you could have used that is now useless because they're the same component. And maybe that was a bad choice. Maybe the local choice you made to be optimal is bad in the global scheme of things. So you can't assume the truth of that statement. You have to prove it. And this is exactly where people think, well, a greedy algorithm will always work. Because it seems like it's the right thing to do. But it's only right locally.
And here we can say that if it is not true, we can.
Good. So now we're talking about a proof. How would we prove that this is in fact the right thing to do? Right? In other words, how do we prove that the minimum spanning tree must contain all safe edges? The standard strategy is assume it doesn't. So let's assume there's a minimum spanning. So let me write the statement out first before we start trying to prove this. Right? So the statement is, L is for lemma, by the way. Okay. Let's assume this is not true. Let's assume an MST does not contain a particular safe edge. So let's draw the picture of what's going to look like now. So what's going to happen is we're going to have one component here. There's going to be another component here, right? We have a tree, so there's some edge connecting these two components, right? But then there was a safe edge, which we did not use. This is the picture of our counterexample to this claim. Okay? Now, what can we say? Yes?
If the cost inside the component is some model that inside the
Yes.
component, then you add in the cost of the other end.
Yes.
And the cost of the safe edge is less than the cost of the
So I can reduce the edge by swapping the two. But I could also reduce the cost by just throwing away the bad edge. So you're about like 95% of the way there. You're correct that by not using the safe edge, we increase the cost. But maybe we had to because we had to maintain connectivity. Is that possible? Is it possible that if we had chosen the safe edge, we would not have achieved the same level of connectivity, the same connectivity that we needed, and therefore we were forced to use the other edge? Can that happen?
No, because it's spanning the inside.
Sorry? Because, yes,
It's spanning the inside of the tree.
they're spanning inside these things. If you have a minimum spanning tree that looks like this, then there's a way to get from here to here using this edge. This is a tree. That means if you now add the safe edge, you have a cycle. Because it's a tree. If you add any edge to a tree, you get a cycle. If you have a cycle, that means any path that originally went through here might as well go through there. It's a cycle. So you can safely remove the black edge without changing the connectivity. So you still get a tree. And you reduce the cost. So if you had a minimum spanning tree that was optimal, it was minimum, and it did not use a safe edge, you could reduce its cost and still keep it as a spanning tree by swapping. But this is a contradiction, because you claim Zoom. So every spanning tree must have all safeties. And that is the proof. Not that, well, we want to do this, but that if we didn't do this, we wouldn't have optimal. And this is what is called an exchange property. This is a very important property. Again, if you know anything on matroids, if you ever read anything on matroids, you'll see this show up in a more abstract form in general. But this is that key property that you must do the locally optimal. Otherwise, you'll be in trouble. Yes.
So is this sort of related to? I'm kind of remembering some of this stuff. Is this related to like if you took the minimum spanning tree or the spanning tree that you got, cut it at any spot, and created two separated components? There would be just one edge crossing those components, and it would be a safe edge.
If it was a minimum spanning tree, yes.
Okay.
Yeah, so in fact, the point that he made was that the minimum spanning tree consists only of safe edges, is sort of kind of true. I mean, at any point in time, there are some edges in limbo. Eventually, they all become safe. Eventually, yes, because of the fact that if you cut it, it better be the cheapest edge. Right? Question?
So what if we have a negative edge weight? I mean, that's...
Oh, no, that's why I said plus. It's
Okay,
always
great.
positive
I
edges.
didn't see that.
Negative edges change and mess up everything. So
Yeah,
that's
that's
not
what I was
something.
thinking.
But, having said that, no, they don't mess up anything at all.
Really?
Why would a negative edge weight mess up something?
Because it would make it so the cheapest cost, immediately wouldn't necessarily be the cheapest cost in the
Why?
long run. Well, I mean, your net, you could have like a -5 and a +4, but then, you'd be at like -1 net cost.
Suppose I look at the most negative edge in my graph. You had a comment? You want to say something?
I was just going to say, it doesn't mess it up because they can't make cycles from spanning trees.
This can't mess up because there aren't any cycles in the spanning tree. That kind of makes sense, but could you explain that? Could you expand on that statement?
Well, one of the reasons that negative edges often just these sort of minimum path things up is because if there's a negative edge and you get a cycle, and you're going around the cycle over and over.
And I think that's probably what you're thinking of as well, this problem with negative edge weights. Right.
But there's no possibility of a cycle here, so you can't keep using the negative edge to keep lower and lower.
And that's a very good intuitive argument for why this might not be a problem. I would not be convinced by your argument, but I feel a bit happier about thinking more about it. But there is a formal reason as well. And there was a hand up in the back. Michelle?
Well, doesn't it cause an issue though?
Ah, good. You have a debate.
You have like three vertices. In order to make a spanning tree, you need to use two of those edges.
Yeah.
And if one of the edges is negative,
Yeah.
then you want to make sure you include that one and not one of the other ones.
Why?
Why? Because that minimizes your.
Why does it matter that's negative? Suppose you're just less than the others. Isn't that still true? Does it matter that, so in other words, we have a number line, right? So you're saying that below 0 is the most special. I'm saying it doesn't matter. All that matters is which one is less than which one. This is not a proof.
Yeah.
I'm just taking your reasoning and saying, why does it matter that it's negative? What's so special about being less than 0? What you're saying is less than the others. They could all be up in the hundreds, and you would still do the same thing you just said.
Right, but okay. If you have like the minimum, what I'm saying is that like the minimum edge or the minimum whatever, the safe edge might not be the best. Like I have like a counterexample, I just can't.
But did I not just prove that the cheapest, that the safe edge is in fact the one you want to pick?
But I'm saying I don't think that's true.
Okay, so let me give you a proof now, which is not as satisfying because I'm not walking you to the proof, I'm just going to give you the answer. Take the minimum weight edge in your input. Let's say it's minus 50 or whatever. Add 51 to all the edge weights. Every single edge weight. So now everything is positive. Okay. If you now look at the cost of a tree in the new graph with all the weights are positive, it is exactly 51 times n minus 1 times the old weight. Because every tree has n minus 1 edges in it. Exactly n minus 1. This is very important. So therefore, the new cost of a tree and the old cost of a tree are exactly related by 51 times n minus 1. So if I minimize the new cost, I'm minimizing the old cost. Because they're exactly the same. They're just shifted. But in the new input, they're all positive. That's why it doesn't matter. So this again not as satisfying as you would like, because I've kind of pulled out the answer by magic. But the intuition is that all that matters is the relative ordering of the edges, not their values. And that we will see this show up in a couple of the algorithms. That it's only the relative ordering that matters. This is not true in general. You can't just take a graph with negative edge weights and add something to all. For example, for shorter spots, you can't do this trick because different shorter spots have different lengths. And now there's no simple relationship between a shorter spot in the new graph and a shorter spot in the old graph, because the number of links might be different. Okay? But for spanning trees, it is true. For this reason, and also because ultimately all we care about is a sorted order. But it's a very good question to ask and a good point to bring up. Okay, so we have two statements here. An MST must contain all safe edges, and as you've already observed, and that maybe you don't even need a proof for. Sorry?
I may have some misunderstanding of this statement. So, my understanding, safe edge is kind of related to the state where you are.
Aha, very good. Yes, it is.
So, this, like when you have an MST, what do you mean by safe edge?
Here's what I mean. Take the set of vertices of the graph, partition them into two pieces, any way you like. I have two sets of vertices. Look at the edges that cross these sets. There's one that's the safest.
Okay.
That has to be the MST.
Okay, I see. Okay.
So a safe edge, you're right, it's described with respect to a stage, but more generally, it's described with respect to any partition of the vertices.
Okay.
So for any partition of the vertices, this must be. If you have a safe edge, that must work.
Why doesn't the same argument work for negative numbers on the edge weights?
Why was there a discussion about negative edge weights?
No. Why can't we use the same reasoning that we use for positive edge weights with negative edge weights?
We can. That's what I just said. It's fine. It works perfectly fine.
Without doing the readjustment off.
Right. So the readjustment is a conceptual readjustment. If you don't believe me that negative edge weights are okay, add them and it's a proof. But you don't have to do anything. It all works because you're only comparing numbers. You'll actually never ever do anything more than compare numbers. So yes. Okay. So the second lemma that we're going to use, which you've already seen, is that and that's it. Once you have these two facts, you can design a whole family of algorithms by virtue of being be safe and don't be useless. And that's it. The correctness just follows almost immediately from these things. All is left to then argue what is running better. Yes?
Doesn't the second one fall from the first one? Because you said an MST contains all safe edges. So it must contain no useless.
But there are edges that are neither safe nor useless.
Oh.
Suppose an edge crosses two components, but is not the smallest. It's not safe, but we don't know yet if it's useless. It might one day be useful. So an edge starts off as unknown. Some edges are safe, some edges are limbo, some edges are useless. A useless edge will stay useless forever in these greedy algorithms because components never split. But an edge that's not safe right now might one day either be safe or useless. Does that answer your question? So there are limbo edges essentially. So at any point in time we have safe edges, we have useless edges, and we have edges in limbo. And we're always going to be picking from, we're going to be picking a safe edge which will change the state of some of the new edges. So we'll make some of them more useless, we'll make some of them safe, and then we'll repeat again. That's at least one algorithm for doing this.
So the limbo edges are between the two components, or?
A limbo edge, for example, yes, is an edge between two components that doesn't happen to be safe. So for example, in this case here, this might be a limbo edge. If I pick that safe edge, this will become useless. If I picked a different safe edge, maybe it'll stay in limbo.
Okay. But if you are picking a different safe edge, then you're not talking about these two components.
Right. This I think will only ever become useless, this particular one. But there's another one, for example, okay, so this one here. This could become safe one.
Okay, yes.
If that green one was a safe edge, then you're right that the blue edge also connecting to the same component can only become useless. Eventually. But the other one could be safe one. So those two blue edges are both in limbo right now. That makes sense? Okay. So now that we are armed with some basic structural facts about minimum, optimal spanning trees, we can now design algorithms. And the simplest algorithm, not the oldest, but the simplest. And this algorithm, I strongly recommend you read the notes on the history of this algorithm, because it's absolutely hilarious. I mean, I put the notes on you last night, so I don't know if you've seen this, but if you will indulge me, which I don't normally do, I also read this. So I was reading this last night, I just started giggling hysterically. So this is, you might have heard of this algorithm, Prim's algorithm, for minimum spanning trees. Some of you know this? Okay. So Prim's algorithm was first described by the mathematician Wojtek Jarnik, not Prim, in a letter to Borówka, which was another Czech mathematician. Then the algorithm was independently rediscovered by Fruskov, and then by Prim, and then by Lobermann and Weinberger, and then finally by Dijkstra. Now Prim, Lobermann, and Weinberger and Dijkstra all knew and cited Kruskal's paper which came before them. They didn't know about Jarnik's algorithm. But Kruskal also had described two other algorithms in this paper. So basically we decided to call this Prim's algorithm, even though Prim had nothing to do with this whatsoever. It's also called a Dijkstra algorithm, even though Dijkstra had nothing to do with this whatsoever. So names are funny things. So this is, yeah, Jarnik's or Prim's algorithm, and it's very simple. It basically says the following. Sorry, I feel like a humanities professor reading notes. So remember we said we maintain a forest and add an edge to it? We're going to do something even simpler. Maintain a tree, not a forest. Then add these. That's it. And repeat. So Prim's algorithm, Jarnik's algorithm, says start with a single node. That's a tree. Find it's a tree, therefore it's a component in my forest. Find its safe edge. What is a safe edge out of a single vertex? It's the cheapest edge connecting this vertex to anyone else. Cheapest edge connecting this vertex to anyone else. Add that in. Now I have two. Now I have two vertices in an edge. What do? Find the cheapest edge out from here. From either of the two. Could be from the first one, could be the second. So you get a new thing. Now I have three things. Find the cheapest thing out of them. Connect it up. Very simple. And again, you may have seen this algorithm. Yes?
It's a technicality, but should we have some sort of stopping condition on the algorithm?
We stop when we have a tree. A minimum spanning tree.
And so
We stop when we have picked up all the vertices.
But I was wondering, that we just applied, I mean, don't do that's still part of the algorithm, right?
Right. No, I should have said that. You're right. But because every tree has n-1 edges, we know we're going to stop at some. It's going to stop at some point. That's it. And we know this is correct. Why? Because this tree only consists of safe edges. If a tree only consists of safe edges, and eventually it picks up every single vertex in the graph, it's a spanning tree that contains only safe edges. Therefore, it's minimum spanning tree. So once you have those two properties in your head, it becomes very clear why this is the correct algorithm. And that's the thing about greedy methods or local methods. You have to set up the system properly. You have to sort of argue carefully about what the structure of an optimal solution must look like. Once you do that, you can then be sure that these will be correct. Until then, you cannot be sure. So how long would this take? N squared. So let's be more precise. With these algorithms, it's important to keep track of the number of vertices, which is V, and the number of edges, which is E.
Either are V and you have to compare the weight between every verse.
Sorry?
So you have to compare every edge with every other edge.
So that would be very expensive. It would be like E squared or something. Or E squared times V. If for every time you add a vertex, you have to do all this.
But if you sorted the edges,
Should be E
then you wouldn't have to do that.
Sorry?
Should be E into it, right?
How?
If I'm, instead of looking from the graph, if I look from every node which I want to add,
Yeah.
it has E edges.
Yeah.
So every,
In total, yeah.
in total, and I'm trying to pick the least.
Yeah.
So it will be like bigger a few times.
So at every step, you look over the set of vertices you currently have. For each of them, look at their neighbors and see which is the cheapest going out edge. And then take the cheapest of all of them. And that will be E times V. Right? So this trivial algorithm would be basically E times V. Because at every stage, and there are n stages, you look at the outgoing edges from every vertex that are not currently in the tree. So in the worst case, you scan all the edges in the graph. So it will be E times V. So this one step.
If you do it from the vertex you're adding, it will be much more easier.
If you do it in the vertex, you're adding it much easier. What does that mean?
If you let's say I have a graph, and then I want to add this vertex in.
Yeah.
I'll see all the edges which are going from these vertices.
Will be the only ones again. But the problem is you could have many vertices that have very large degree of theta E. So that itself is not enough. But you're getting closer to yes.
Also, if we actually mark the graph, the edges that we previously examined, the runtime of that would become lower.
They would, but again, this won't change things asymptotically. It'll change the constant factors, but it won't change this overall running time. These two ideas will speed things up, they won't speed things up enough. But the observation is still true that when you add a new vertex, those are the only edges that could affect things anymore, because that's the new change you're making. So it turns out if you make, if you keep all the edges adjacent to the current tree in a priority queue, and always pick the cheapest one, you can do this in log V time, and you can do a bunch of updates. And so there's a bit more detail here, but basically you can replace this step here. Let's see. So Ezekiel. Yeah, so basically you can do this in E log E time instead of E times N. So it'll be something like, which is basically E log E. You basically maintain a priority queue of all the edges adjacent to the tree. You pull out the cheapest one and check if it's going out from this, add it, and then you want more. Again, there are details here that I'm not going to get into right now. Some of these. But this algorithm is kind of is one way to think about how you might go about growing your minimum spanning tree. And I think people were sort of hinting at what might be another way to go about this, which again you may have seen, which is called Kruskal's algorithm. Which is basically sort E in increasing weight. And then add edges in order if they are safe. So sort all your edges in increasing order of weight. Why is this a good thing? Well, clearly the first edge you pick, the cheapest weight edge, must be safe, right? Because it's the smallest weight edge in the graph. Yes? So you add that in. Now you look at the next cheapest edge. It might be somewhere else. But this has to be safe. Why? Because if it doesn't form a cycle or anything with what you have already, it's connecting two things, and this was the cheapest way out for one of them. So by definition of safety, this has to be a safe edge. And you keep doing this. At every point, if you add a new edge, there are two things could happen. Either you keep a tree, in which case it must be safe, or it adds a cycle, in which case it's useless. Don't add it. So Prim's algorithm starts off with a tree and always grows a tree. Kruskal's algorithm is more disorganized. You'll have like a bunch of floating components everywhere that they get connected up. But they're always getting connected by the cheapest cost edge between them. And so you're always adding safe edges. And that's nothing. And again, there's some data structures you need to do to make sure when you add these things, you can maintain the information. It's basically unifying data structure. And the sorting is the biggest time in this whole process. And that takes basically long.
Even to find out whether it's qualified, even lowest edge qualified, if it's formally closed.
The lowest edge always qualifies. It's the cheapest edge. It has to.
No, but after it might become cyclic, right?
Okay, so then what do you have to do? What you're doing is then you're saying, given a new edge, does it connect things in two different components or the same component?
Exactly.
That's a unifying data structure.
Oh, the data structure.
Yeah. You just say, okay, what is the component ID for the two endpoints?
Okay.
Yeah. And then when you merge things, you update the component. That's why you need some kind of tree structure. You can use a unifying if you want to be really clever. You can use something simple. Doesn't really matter. You just pay log time each. Okay. And that's it. Yes.
So the question is, how do you find all of the edge weights sufficient?
It's given to you. It's given to you in the input.
Oh, it's given.
I give you the graph, and every edge is written. I have the weight written down in every.
If you were just given a set of nodes
with no edge weights,
and with no edge weights, you'd have to calculate all the edge weights.
It's a very good question. So, for example, one situation where this comes up is if I want to compute a minimum spanning tree in the plane. So I have a bunch of coordinates, xy coordinates. I have a normal way of measuring distance between 2 points, and I want to compute the minimum spanning tree. Here, I'm not given the edges. I could write them all down, but that would take too long. In fact, you can do this faster. So you can actually do the minimum spanning tree calculation without writing down all the edges. So you can do a lot better than this. But in the graph case, you don't know anything else. You have to have all the weights. And by the way, this is why it doesn't matter with your negative weights. All I'm doing is sorting. It's a relative order that matters, not the absolute values. Yes?
So how do you come up with the complexity of E log B? Shouldn't it be E log E?
But how big is E? How big can E be maximum? E can be at most V times V minus 1 over 2. Right? So, good.
Sorry, the same logic can be applied for before log you have E, right? The same logic could be applied there as well.
Where?
Then it becomes log V square.
Yeah, so I just plugged in, since E is O of V squared, log E is O of log V squared, which is 2 log E.
Yeah, but before you have an E, right?
Yeah.
Instead of that, I can put V square there.
Well, log V squared is equal to 2 log E, yes. I mean, I'm trying to relate E and V. In log factors, they're basically the same.
Yes, but there's a term before log, which is just E, right?
No.
E into log V. Right?
Log of E.
No, that
2 lines up.
2 points up.
There, E log V.
E into log V, right?
Yeah.
That E could be written as V square, right?
Yes, but I don't want to, because E could be much less than V squared. E is less than equal to V squared. If I'm a sparse, okay, a tree has how many edges? A tree on V nodes has V minus 1 edges, not V squared. In fact, sparse graphs are a source of great interest in real world graphs. Social networks are all very sparse. E is not V squared, it's much, much less than V squared. It's like V to the 1 plus epsilon or V log V or something very small.
But why did you use that for log? What I'm curious is...
What I'm saying, here's why. Because in terms of the log, they are constant factor related. And we ignore constants for now.
Okay.
But asymptotically, E and V are quite different. E could be V squared. That is asymptotically very different from V. factor away from B. It's much away from B. So you want to distinguish E and B as two different terms. Yes, in the worst case, it's B squared log B. But maybe I can give an algorithm that's much more sensitive to the number of edges and runs faster if the number of edges is less. I would like to know that. In the log factors, this won't make a big difference. Yes, a small factor it will make, not a huge difference. But in this, it will make a big difference, yes.
So it seems that the Prim algorithm would be very suitable for making powerful requests.
You would think that, yes, and that's a good argument that Prim's algorithm seems to be very slow. It's heavily sequential. Even though it has the same running time as Kruskal's algorithm, which might, well, Kruskal's algorithm you have a sort, which you can do in parallel. And then you might be doing something more, and that's good. The next algorithm I'm going to describe, which is the sort of the granddaddy of all these algorithms, which came before, but people didn't realize it was, is much more parallel friendly. And let me explain that. I should mention one side note. There is a talk tomorrow, a colloquium in the CS department. It will be in Web 1230, right there. By Mike Goodrich from UC Irvine. If you're in the CS department and you're on the mailing list for colloquium, you've probably seen the announcement for this. This is a new algorithm for sorting. It's a new algorithm for parallel sorting, in fact. And it's data oblivious. It's an algorithm for sorting, basically, that doesn't look at the data at all. It's like a circuit. It's like a bunch of wires. You just plug any input to it and you get the answer, which is very cool. That means you can hardwire it completely. And it sort of improves a result that's been known for 30 years but had horrible consequences. I think I mentioned this before. So if you can, if the time works out for you and you can make it, I would encourage you to attend the talk. Mike Goodrich is a great speaker. It'll be a lot of fun. So, but again, you may have class to know, but if you have time, tomorrow 10 o'clock in Web 1230. I was reminded of that by a parallel statement. So, these two algorithms are what you typically learn in the undergrad algorithms class. At least historically, that's what people thought were the two main algorithms for MST. But it turns out that some many years ago, people discovered that back in the 20s, Borufka had designed an algorithm that was much more general than both of these. And it works like this. And in our current knowledge of how to do this, it's very easy to state. So the Borufka algorithm I've got some of the accents wrong here, so I apologize in advance for that. Says something which is even simpler than this. It says, oops. That's it. Don't add one or wait for a tree or do just add everything you can. All edges that are simultaneously safe right now, add them all in. And then repeat. No. These are greedy algorithms. There's no deletion at all. You don't go backwards, you always go forward.
So you stop when there's no safe edge?
You stop, yeah, you're guaranteed to keep going till there is no safe edge left, at which point you have everything connected up. So it's not too different from Prim's algorithm. There you had a tree, you're adding one safe edge element there. He's like, whoosh. Then whoosh, you just keep going.
How do I know they are safe edges before comparing them?
You have to do some work to find the safe edges. I'm not saying that there's no work, but that's how it works. So now you can ask yourself, okay, how do I find all safe edges? So at some point, again, I have some graph and I have some state of the algorithm. So I have some components like this. They're all disconnected, right? How do I find all safe edges between these things? Yeah.
Wasn't there only one safe edge because you have nothing inside of your component? Or inside any components?
You have nothing inside any component. In the beginning, you have a bunch of vertices. They're all individual components by themselves.
Okay.
So in the beginning, you start with every vertex in a separate component by itself. Yeah.
So you visit each vertex and find its safe edge and that separate safe edge?
Well, safe edges are defined per component, not per vertex. Sure, but in general, I have components. I want to design an algorithm that works in general. So I want to design an algorithm that works at my current state, whatever it happens to be.
Visit each component and find its safe edge.
Sure. So let's assume we have all the vertices all dispersed nicely. For each vertex, we know what components it is. So here's what you can do, right? You look at every edge and look at the labels of its endpoints. If its endpoints on the same component, this edge is. Right? So if I have an edge in my graph that looks like this, it's a useless edge. I can throw it away. If I have an edge that goes across components, it's a candidate for being a safe edge. We don't know yet if it is, but it's a candidate. So we sort of record that edge and its current value in the current updated claim for the safe edge going out of this particular component, and we'll see if it in fact is a minimum or not. So basically what you maintain is you maintain an array. So let's say there are, let's see how many. Yeah, so let's say you have these many components. You have an array that contains one entry for each of these components. And what it stores is the safe edge going out of this component. And you scan the entire graph, scan all the edges to figure out if this is going to be a safe edge for this component. So you basically at some point you take an edge. If it's between two components, you look at the current values of the safe edge and you decide, okay, is this going to be safe or not? If it is, you update. If it's not, you throw it away. Right? It might update both of them, it might update one of them, it might update neither of them. Right? And you do this. At the end, you know all the safe edges for each component. You can add them all. Yes?
So when you say the safe edge, so when I think of safe edge, it's you have to have two components and it's the minimum weight.
No. A safe edge is an edge going out of a component.
Right.
To anywhere.
Okay, right.
Right. There could be the cheapest edge from me to that component, the cheapest edge from me to that component, but one of them is the cheapest.
Right. Okay.
That's my safe edge.
Okay, right.
Yeah. So there's only one.
Okay.
That's very important actually.
Excuse me.
Yes.
Here the component is just one point, one node.
No, this is at some stage of the algorithm. I have bags. I have a whole forest.
First stage is
At the first stage, everything is one. Yes, but later on, it gets to be different things. Yes.
Is it because you add all the safe edges together, you never need to delete the unsafe edges?
Well, because you add all the safe edges together, you don't have to add them one by one. But they're all safe at the same time, so it's safe to add them. So to speak.
Yes, and that's
one of them cannot make another one unsafe. Yes.
And
So you can.
no need to delete at later point compared to the other algorithm.
But I don't delete anything anywhere else. None of the algorithms ever delete an edge. Once you add it, it's in forever. It's like a secret society, right? Once you're in, you're in. In none of the algorithms I described did you ever delete an edge from the tree. In Prim's algorithm, you take a tree, you keep adding edges, and you're done. In Kruskal's algorithm, you keep adding edges, you get these forests, at the end you're done. You never ever delete. And here also I'm not deleting. These are greedy.
You have a bank of potential edges that are not being added.
Yes.
So you're not deleting an edge, you're just not using one of them.
Correct. Correct. Maybe you think of delete as saying it's useless.
Yeah.
Okay, so it's not deleting. I don't think of it as deleting. It's more like you declare it to be useless altogether. Right? It was never a member in the first place. You know. So maybe it's a semantic difference between us. But I think of deletion as you put it in and you have to change your mind. I never change my mind. I can make a local decision for any edge saying it's useful, now I'm going to put it in, or it's useless, I'm not going to put it in. Yeah? Okay. Yes?
So you said each of those boxes, or you're keeping track of the safe edge out from a certain...
Each of the components.
You can also have multiple safe edges.
No, you can't. That's what I'm saying. The safe edge is defined as the cheapest edge out of my component. Not out of my component to that component. So there's only one.
What do you mean by because if I do that, then I almost know the answer. Right?
I should say recurs. I mean, another way to say it is just repeat. So you do, okay, so what's going to happen? You're going to do this thing, you're going to find all the safe edges, You're going to add all the safe edges. What's going to happen? Your components are going to collapse. So now you have a new set of components. Repeat. So imagine what happens in the beginning. Right in the beginning, every vertex is by itself. And everyone looks around, sees who their closest neighbor is. Okay? I have a closest neighbor, someone else is a closest neighbor, someone else is a closest neighbor, and so on and so forth.
So in one shot, if it forms, you should get an instant.
It might.
Because two vertices could just, their shortest edges to each other.
Exactly.
They become isolated.
And that's the worst case scenario, where two vertices just look at each other.
But then there will be a third vertex trying to link to one of these.
No. Okay, so for example,
Just have pairs.
For example, suppose the graph consists of U2 and U2. He's closest to him. He's closest to him. They link up.
Okay.
You two are closest, you link up.
Okay.
After that,
Then.
the edge will be between you and you.
Okay. Yeah.
And this in fact is a worst case scenario. You have pairs of things linking up. But in general, what could happen is if you have a chain like this, you could link up here, and you could be slightly, you could link up there, and you could link up there, the whole thing could come in one step.
Yeah.
Maybe. But maybe it's not, we don't live in the business of maybe. So again, the algorithm is find the safe edges out of components and add them all in. Prim's algorithm said, no, it's okay, that one, like, no, it's not that one. Okay? And so all that remains then is to figure out how long this is going to take. Because we're always adding safe edges, so correctness-wise we're fine. Now you can compute these safe edges in one scan of the edges. So each iteration takes E time. The question is how many iterations do you need? This is a bit more complicated. In the other algorithms, you do at every step you add something in, so you make progress, so there are n steps overall, and you can reason about that. Here you can't do that because you're doing a whole bunch of stuff in one shot.
So the worst case, though, you have the problem.
The worst case, you halve the problem. What does this sound like?
T by 2E every time.
At every step, you reduce the number of vertices by a factor of 2, or number of components by a factor of 2. How many iterations will you need? I didn't hear a single sound, which means there are disagreements.
Log n base 2?
I heard of log n base 2. What else? Anything else? Is any other candidate for an answer here?
Well, n doesn't make sense if we're talking about edges and vertices.
Sorry, log v. Yeah, you're right. Log of the cardinality of v. So, any other answers? Careless shorthand we use often is that v is called n and e is called n. But I'm not right. You're right. Log v. So it will take you log v iterations to n, because in every step, in the worst case, you half the number of things. It could be much more, but it's no less than half, because you could have spares. And so e iterations per step, this takes and this is a bit more parallel friendly, because you can add all safe edges in parallel. I'm not saying you can make this parallel directly, but it seems like it's possibly more parallelizable. And these are all good things to observe to say, okay, when can I parallelize my method? We were talking about this just now. Right? And in fact, this algorithm gets used a lot more in distributed parallel implementations of FST than the other ones for this precise reason, that you can do these local decisions simultaneously and make progress. So the amount of work, the number of parallel steps is basically log v. Questions?
For the time I understood log v, did not know how the E came.
Because what we're going to do is in every step, we're going to scan all the edges one by one. For each edge, we're going to first figure out is it useless or not. If it's useless, we stop thinking about it. If it's not useless, it connects to components. We are currently maintaining the safe edge out of every component. We update that safe edge based on new information given by this edge. Is this edge cheaper than the current safe edge out of this component or not?
Okay.
If it is, we update. If not, we don't. So it takes constant time per edge.
But in constant time per edge per node, right?
Not per node, per edge. Because each edge only connects two components. We only have to look at those. It won't affect anything else. So I have been a little bit fast and loose with the analysis of join times. This is partly because it's all the nodes. and partly because I wanted to focus on the fact that a simple design principle or simple observation about the structure of the optimal solution leads to these algorithms. They all run E log V time. Some of them take E log V with a bit more work, some of them take E log V with a bit less work, but they're all the same. And in a different kind of setting, I would spend a lot more time describing the details of the algorithm. But I'm trying to get you to think more about local operations and focus on that now. But having said that, all the analysis in detail is in the notes. So you have the information, and feel free to post questions in the forum if you have any more confusion. Yes?
Seems like this one has the potential for having a better average case run time. Prim's and Kruskal's algorithms seem to have, I guess I think about it a little bit more, seem to have a consistent running time. This one has a potential for performing better than that.
So Kruskal, I think, is very consistent because you just sort and it's a deterministic strategy. Prims, you could imagine variation based on where you start. Because there's the non-deterministic part of Prims is, okay, which one do I start? Which vertex do I start with? Maybe if I pick something, the evolution of the tree is different if I pick something else. It's possible it might take a bit longer. You're right, though, that this has a feel of something that could actually be very flexible to the data and could be much more responsive to what's happening in your graph. And that's partly why this is the one that gets used, again, for parallel implementations, gets used for randomized implementations, and things like that. So that your intuition is kind of on the right track. Yeah. I mean, I can't say this formally, but there's that kind of feeling, yes. All of these algorithms run essentially E log V time. And in some sense, if you're only willing to look at edges by comparing them and looking at their relative ordering, which is all we're doing here, then you can't do any better. Just like for sorting, if all you're willing to do is compare two numbers and tell me which one is bigger or smaller if they're equal, you can't do better than n log n comparisons. But you can do better if you do more things with the numbers. Here, if you're limited to this, you can't do any better. And there have been attempts to sort of push how far you can get. We still are not quite yet at a deterministic algorithm that runs in linear time for the minimum spanning tree. Not yet. But there are randomized algorithms that toss coins that do run in linear time in expected sense. And we might see some of them later on when we talk about randomization. But this is still, that's such a basic problem. This is not really fully resolved. We're still puzzling over what the best ways to go about solving these problems. So this ends what I think of as kind of the first phase of this class, in the sense that we're looking at core techniques that, again, if you've done an undergraduate degree in CS, you've probably all seen before. VD algorithms, data programming, divide and conquer references. Hopefully I've given you a different perspective on these, but you have seen them before. What we're going to do next, and I've put up links to the material, is what we call flow algorithms, which are both fundamentally a different way of thinking about algorithm design. They require different ways of thinking about problems, and they're also things you may not have encountered. How many of you have seen network flows algorithms before? Yeah, so some, but not all. That's what I thought. So that's where the material is going to change a bit. It's going to be less familiar. It's going to get a little more complicated, and it's not going to fit into all these nice paradigms. Flow algorithms are not greedy. They're not dynamic programming. They're not dividing confidence. They're very different. But they're also very, very useful. There are many problems for which it will seem like it's impossible to solve efficiently, but once you have flows. So we'll talk about that. So don't forget the lecture, the special colloquium tomorrow if you can, 10 o'clock in Web 12:30. It's about sorting in parallel. And we'll see you.